So when you're dealing with unit and conversion problems, it's always a good idea to become familiar with the equations and the unit names that you will be coming across in your specific problem set. In this case, we're going to be dealing with some basic electrical engineering units and some not so basic ones. So as we move in to the following problems, I'm going to keep this little cheat sheet handy so that we can identify the variables that we're given, what we need to find, and the equations that we can use to link those two together. Alrighty. So in this first problem, we are given a piece of silicon that is doped with 10 to the 16 boron atoms per centimeter cubed. So boron, if you remember, has one less electron than silicon, meaning it is an acceptor. It can take in additional electrons and create holes within our silicon, making a p-type silicon. So over here, we know Na is our acceptor density. So let's go ahead and write 10 to the 16 per centimeter cubed. So that's centimeters to the -3. That just symbolizes that it's dividing by centimeters cubed. So we also know the piece of silicon itself is only 200 by 150 by 50 nanometers. So that is our volume right there. We're given density and volume, although in different units. And we need to find out how many boron atoms are in the piece of silicon. So this is our density of boron atoms, and we need to convert that by multiplying by the volume, since density times volume is equal to our amount. So let's go ahead and do that. We want to find number boron atoms. There's no specific variable for this kind of equation. So let's see, we have our acceptor density that is 10 to the 16 boron atoms per centimeter cubed. And then we want to multiply that by our volume. So let's get our volume ready. So that's 200 times 150 times 50. So that's 1,500,000 nanometers cubed. So we're multiplying per centimeter by nanometers, so we're going to have to convert first. I think the easiest way to do this would be to just convert our centimeters term into nanometers. So let's put let's see, there are 10 to the 2 centimeters in 1 meter. This is centimeters cubed, so we're going to be cubing this, right, like that. And then within that, there are 10 to the 9 nanometers within 1 meter. And we're cubing that to get our nanometers cubed. So now we can multiply by our volume over here, the 1,500,000 nanometers cubed, and there are no additional units needed because, as we can see, our centimeters cancel out here, nanometers cancel out here, and we are left with just the number of boron atoms. So if we do this real quick, we get 15 boron atoms, which is not a lot at all, but this is a microscopic piece of silicon, so it kind of makes sense. The next part of this question is to find out how many mobile holes are in the silicon. If you remember from over here, our mobile hole density, P, is defined as the boron or acceptor density plus the intrinsic carrier density of the silicon. So that's just how many holes the silicon has that are created by created thermally before it's even doped. So we have our Na of 10 to the 16, and we're adding the intrinsic carrier density of silicon, which is commonly 10 to the 10. And in most cases, since 10 to the 16 is so much greater than 10 to the 10, we just ignore it. So in this case, I'm going to go ahead and say that our hole density is the same as our acceptor density, and if we plug that in over here, that means we have 15 holes, the same amount as our boron atoms. So in this next question, we have a copper wire with a length of 50 meters. So let's go ahead and write length equals 50 meters. And it has a current running through it with a density of 100 amps per centimeter squared. So that's our current density term there, J. Let's write that down. 100 amps per centimeter squared. We need to find the voltage difference from one side of the wire to the other. So we're trying to find V, our voltage. And we know that the conductivity sigma, is equal to 6 times 10 to the 7 Siemens per meter. So let's see what equations we can use to link these together. We know that current density is equal to sigma times electric field. We don't have any information about the electric field, but just above this equation, we see that the electric field is actually equal to voltage divided by length, or distance. So if we just plug this in, J equals sigma V over L, this is all our terms here. We're trying to solve for voltage again, so let's just get that on the right side, or left side rather. So that ended up being J L over sigma was V. We can just keep it there. So now we need to write out our little dimensional analysis. So starting off with current density, I'm going to put 100 amps per centimeter squared. And then we have length. This is in meters. And we're also given conductivity in Siemens per meter. So I think it's probably easiest to convert to meters from this centimeter squared term. So let's go ahead and do that. We have 10 to the 2 squared centimeters squared in 1 meter squared. I am running out of space here. I will just move this. So now we have it in terms of amps per meter squared. So let's go ahead and add our second term. That's length. So we know the length of the wire is 50 meters. So we have one of those meters canceling out. So now we just have amps per meter. And we need to get to volts. So next we divide by our conductivity. So we're going to put it on the bottom. 6 times 10 to the 7 Siemens per meter. We put the meters on top because it's dividing. And if we plug all this in, we can get our final answer. Which is 0.8333 volts. Write that out. And I'm gonna go and shove this up here. Alrighty. So in this next question, we're given that we have a conductor with a cross-sectional area of 20 millimeters squared. So let's go and write out our area is equal to 20 square millimeters. And we know over a span of 10 milliseconds, so this is our time. Let's write that out. Our change in time. 4 times 10 to the 15 electrons pass through the conductor. So that is not the same as change in charge. This is number of electrons. So let's see, number of electrons. There's no good variable to call this. It's 4 times 10 to the 15. And we need to find the current density in the conductor. So that is J. So we're given number of electrons, and using this first equation, we can use that to find the change in charge. And dividing the change in charge by the change in time, we can get current. And we're trying to find current density, which is just our current divided by our area, which is also provided. So let's write this out. We have the current density is the current divided by the area. Our current is just our change in charge divided by our change in time. Keep that A in there. Our delta Q is the fundamental charge, 1.6 times 10 to the negative 19, times our number of electrons. All still divided by delta T times A. And that is our final equation. We can now plug in everything. So let's start with our small q. 1.6 times 10 to the negative 19 coulombs per 1 electron. And then we're multiplying by the number of electrons. So that's 4 times 10 to the 15 electrons. Those will cancel out right here. That is a simple unit. And we're dividing by time. So 1 over 10 milliseconds. For current, we're going to have to convert to seconds. So let's say we have 1,000 milliseconds in 1 second. And then running out of space again. dimensional analysis really gets big. We are dividing by our area, which is 20 millimeters squared. I'm going to move this out of the way. They want our answer to be in terms of centimeters squared up here, amps per centimeter squared. So we're going to have to convert these millimeters squared to centimeters squared. So that is 10 to the 3 millimeters in 1 meter. We're squaring because it's millimeters squared. And then divide by the number of centimeters. So that's 10 to the 2 in 1 meter, 2 centimeters squared. Alrighty, and this should yield our final answer. If we just plug all this in. And we get a final current density of 0.32 amps per centimeter squared. Okay, in this final problem, we're given that a p-type piece of p-type silicon is doped to 10 to the 18 atoms per centimeter. Doping atoms per centimeter. So this is p-type, so that means they are acceptor atoms. They're making a positive charge, P for positive. So this is Na. So right, Na equals 10 to the 18 per centimeter cubed. The electron mobility of silicon is 1,000 centimeters squared divided by a volt second. And the whole mobility is 450 centimeters squared divided by a volt second. So these are our carrier mobility terms. So we can write that as mu n for our electrons, 1,000 centimeters squared per volt second, and mu p for our holes, positive, is 450 centimeters squared per volt second. We need to find the conductivity of the p-type silicon. So that's our sigma. So if we look over here, we see that sigma is equal to Q in mu. This is our electron density right here, but as we can see, this is p-type doped. So there are going to be many more holes than there are electrons, because from this equation here, Np equals Ni squared, we can solve for P real quick. That'll be our 10 to the 18 plus our intrinsic, which is just so insignificant. We just round up, or round down rather. And our n, we can solve from there as n times 10 to the 18 is equal to Ni squared for silicon, and the intrinsic density is 10 to the 10. So we get n times 10 to the 18 is equal to 10 to the 20. So that means n is only equal to 10 to the 2. So we barely have any electrons, or mobile electrons, in this p-type silicon here. So we are going to have to rearrange this conductivity equation to reflect the conductivity of our holes. So we'll do the fundamental charge again, that doesn't change. But instead of electron density, we're going to put our hole density, since that is the dominant dominant carrier in our silicon. And then instead of electron mobility, we're going to put the hole mobility. So basically just replacing stuff with P. And it looks like we already have everything we need here, so let's just go ahead and start plugging and chugging. We get 1.6 times 10 to the negative 19 coulombs. I'll just say carrier. Doesn't have to be electron specific. Applies to electrons and holes. Times our hole density, or our positive carrier density rather. That is 10 to the 18 divided by centimeters cubed. Now we have our hole mobility. We want to use the hole mobility, which is this 450 right here. So we're multiplying right here. And that is everything. If we multiply all these together, we should get our conductivity. And we get 72 Siemens per centimeter. It asked for Siemens per meter though, so we're going to have to make another conversion. We end by multiplying our centimeters squared, or centimeters cubed, by centimeters squared, we end up with just per centimeter. So to cancel out the centimeter, we're going to put 10 to the 2 centimeters divided by 1 meter, which is the same as 7,200 Siemens per meter. Alrighty, that's all.